Reality is not what it seems. The Journey to Quantum Gravity by Carlo Rovelli. Picture this. It's 450 BCE, and a man named Leucippus is boarding a ship in the bustling Greek port of Miletus. The salty Mediterranean air fills his lungs as the vessel sets sail for distant Abdera. This might seem like an ordinary voyage, but what Leucippus is about to set in motion is anything but ordinary. He's embarking on a detective story that will span more than 2,000 years, a thrilling quest to answer perhaps the most mind-blowing question we can ask: what is our world actually made of? This ancient journey is where physicist Carlo Rovelli begins his absolutely remarkable book, Reality is Not What It Seems. Rovelli isn't your typical lab coat-wearing scientist. He's one of the founders of loop quantum gravity, and he has this rare, almost magical ability to take brain-melting concepts about the universe and explain them like he's telling you a story over coffee. In this book, he takes us on an incredible ride through human thought, starting with the first sparks of scientific reasoning in ancient Greece and zooming all the way to the cutting edge of modern physics. And let me tell you, this journey will shake everything you think you know about reality. That solid floor you're standing on? The steady tick of your watch? The space you're moving through right now? None of it is what it seems. These are beautiful illusions, mental shortcuts our brains have created to help us navigate a reality that's far stranger, far more mysterious, and honestly, far more magical than we could ever imagine. Here's what I'm promising you today. By the time we finish this journey together, you'll see the universe in a completely different light. You'll discover that reality isn't some static stage where things happen, but rather a shimmering, dynamic web of events. You'll learn that time doesn't actually flow the way you think it does, that space is made of impossibly tiny, indivisible grains, and that things only exist in relationship to other things. It's an absolutely breathtaking vision, pieced together by some of the most brilliant and rebellious minds in human history. And it all starts with that simple ancient question: what is everything actually made of? Our adventure begins in that vibrant ancient city of Miletus, 26 centuries ago. For thousands of years before this moment, whenever people wondered where the world came from, the answers always involved gods, spirits, and mythical creatures. But something different started happening in Miletus. A group of thinkers, led by a man named Anaximander, decided to try something radical. They would look for answers not in fantasy and mythology, but in observation and reason. They believed the world could be understood. This was the moment scientific thinking was born. This spirit of inquiry is exactly what drove Leucippus on his voyage. When he finally arrived in Abdera, he teamed up with a brilliant young student named Democritus, and together they proposed an idea that was both stunningly simple and incredibly powerful. The entire universe is made of just two things. First, empty space, a boundless void, and second, an infinite number of tiny, indivisible particles moving through it, which they called atoms. Everything we see around us, they argued, the churning sea, the stars overhead, our own bodies, even our thoughts and emotions, is just different combinations of these atoms. Democritus put it beautifully. Just as comedies and tragedies can be written using the same few letters of the alphabet, the endless variety of the world is created by the endless combinations of atoms. It was a vision of breathtaking simplicity. But it raised a deep, troubling question that would haunt thinkers for the next 2,000 years. Here's how Democritus thought about it. Imagine that matter wasn't made of atoms. Imagine it was perfectly smooth and continuous, something you could divide forever. If you broke a piece of matter in half, and then in half again, and kept going an infinite number of times, what would you end up with? You couldn't be left with tiny pieces, because that would mean you hadn't actually divided it infinitely. You'd have to be left with points that have absolutely no size at all. But here's the puzzle. How can you build something with size by stacking together points that have no size? You can't. It's impossible. Therefore, Democritus concluded, the division must stop somewhere. There must be a smallest, indivisible piece. the atom. This problem of smooth versus chunky, continuous versus granular, was famously captured in a paradox by a philosopher named Zeno. Imagine the swift hero Achilles racing against a slow tortoise. The tortoise gets a head start. To catch up, Achilles must first reach the point where the tortoise began. But in the time it takes him to get there, the tortoise has moved a little further ahead. Now Achilles must cover that new, smaller distance. But in that time, the tortoise moves even further. This pattern continues forever. Zeno argued that, logically, Achilles could never catch the tortoise, because he'd have to cover an infinite number of distances, no matter how small. Of course we know Achilles wins the race, so what's wrong with the logic? Leucippus and Democritus offered a radical solution. Maybe you can't divide space and time forever. Maybe there's a smallest possible distance, a smallest possible moment. Maybe the world, at its deepest level, isn't smooth like butter, but grainy like sand. For over 2,000 years, this idea of atoms remained just a philosophical speculation. Brilliant, yes, but with no proof whatsoever. Then, in 1905, something extraordinary happened. A rebellious 25-year-old working in a patent office in Switzerland provided the proof that had eluded humanity for millennia. His name was Albert Einstein. He noticed something peculiar. Tiny grains of pollen suspended in water seemed to dance and tremble for no apparent reason. This phenomenon, called Brownian motion, had been observed before, but no one understood why it happened. Einstein had a revelation. The pollen was being jostled around by invisible, microscopic particles, the molecules of the water itself. If the water were perfectly smooth and continuous, the pushes from all sides would cancel out perfectly, and the pollen would sit perfectly still. But because the water was made of a finite number of tiny atoms, the collisions were never perfectly balanced. By carefully analyzing this random dance, Einstein was able, for the first time in history, to calculate the actual size of atoms. After 23 centuries of wondering, Democritus was finally vindicated. Matter is granular. This confirmation set the stage for the first of two great revolutions in 20th century physics. But before Einstein would turn our understanding of the cosmos upside down, another critical piece of the puzzle had to fall into place. For centuries, the world of physics was dominated by one towering figure, Isaac Newton. Newton had taken the ideas of Democritus, a world of particles moving through vast, empty space, and given them tremendous mathematical power. He described a universe that ran like a perfect clockwork machine. Space was a fixed, unchanging stage, and time was a universal river flowing at the same rate for everyone, everywhere. In this clockwork universe, objects moved because of forces, like the mysterious force of gravity that somehow reached across the emptiness of space to pull the moon toward the Earth. Newton's vision was incredibly successful. We still use his equations today to build bridges and send rockets to Mars. It seemed like he'd discovered the final, ultimate laws of the universe. But here's the fascinating part. Newton himself was deeply troubled by his own theory. How could the Earth possibly attract the moon without anything physically connecting them? He called it an absurdity, and left the question for future generations to solve. The answer came from an unlikely source, a humble, self-taught genius named Michael Faraday. Working in a London laboratory in the 1800s, Faraday was experimenting with electricity and magnetism. As he played with magnets, feeling their invisible push and pull through the air, he began to see something new in his mind's eye. He imagined that space wasn't empty at all. It was filled with invisible lines of force, like threads woven throughout the universe. He proposed that an electric charge doesn't act on another charge at a distance. Instead, it creates a disturbance in this invisible entity that spread throughout space, and this entity then acts on the other charge. Faraday had just invented the revolutionary concept of the field. A brilliant Scottish mathematician named James Clerk Maxwell took Faraday's beautiful, intuitive vision and translated it into a set of elegant equations. And when he worked through the mathematics, he stumbled upon one of the greatest discoveries in the history of science. Maxwell's equations predicted that waves could travel through this electromagnetic field. He calculated the speed these waves would travel, and the result was absolutely astonishing. It was exactly the speed of light. In that moment of realization, he understood. Light is a wave rippling through the electromagnetic field. The vibrant colors we see with our eyes are just different frequencies of this wave's vibration. We don't actually see Faraday's lines of force. We see them vibrating and dancing. The Newtonian world of empty space was suddenly gone, replaced by something far richer. Reality was now made of two fundamental things: particles and fields. This discovery set the stage for the true revolution, and at its center was that same young man from the patent office, Albert Einstein. Einstein realized there was a deep, disturbing conflict between Newton's physics and Maxwell's new theory of light. According to Newton, speed is always relative. If you're on a train moving at 50 miles per hour and you throw a ball forward at 10 miles per hour, someone standing on the ground sees the ball moving at 60 miles per hour. Simple addition, right? But Maxwell's equation said something completely different. The speed of light is constant and absolute. It doesn't matter how fast you're moving, whether you're standing still or racing through space at incredible speeds. You will always measure the speed of light to be exactly the same. This seemed like a complete and utter paradox. For 10 long years, Einstein obsessed over this problem. He thought about it constantly, turning it over in his mind from every possible angle. And the solution he finally came up with, in 1905, forever changed our understanding of space and time. This was his theory of special relativity. Einstein's profound insight was that space and time are not separate and absolute, as Newton believed. They're actually interwoven into a single fabric, spacetime. And this fabric can be stretched, squeezed, and distorted. One of the strangest consequences of this realization is that the idea of now is not universal. It's not the same everywhere in the universe. Imagine you have a friend living on Mars. Here on Earth, we have a crystal-clear idea of the past, the present, and the future. 3 distinct zones, neatly separated. But Einstein discovered that for your friend on Mars, there's what he called an intermediate zone. Because it takes time for light and information to travel between you and your friend, there's a period of about 15 minutes on Mars that is neither in your past nor in your future. It's an extended present, a fuzzy zone where the concept of now breaks down. This means that the concept of a single, universal now that applies to the entire cosmos is actually an illusion. It's an illusion created by the fact that here on Earth, this intermediate zone is so incredibly tiny, just a few billionths of a second, that we simply can't perceive it in our daily lives. The fusion of space and time into spacetime had another, even more world-changing consequence. Just as space and time turned out to be two facets of one thing, Einstein realized that energy and mass were also two facets of the same underlying entity. They could be converted into one another, according to the most famous equation in all of science, E = mc squared. Because the speed of light, c, is such an enormous number, this equation tells us that even a tiny amount of mass can be converted into a tremendous amount of energy. With this single line of mathematics, Einstein had unlocked the terrifying and awesome power of the atom and ushered humanity into the nuclear age. But Einstein wasn't finished, not even close. He knew his theory was incomplete. It worked beautifully for describing motion and light, but it didn't include Newton's mysterious force of gravity. So he set out on another 10-year journey of intense thought, a relentless quest to understand the true nature of gravity. And the theory he produced in 1915, the general theory of relativity, is often called the most beautiful of all theories. Einstein's stroke of genius was to connect two seemingly separate problems. The first was how to describe gravity as a field, following Faraday's brilliant insight. But the second problem was deeper and more philosophical. What exactly is space? For Newton, it was just an empty, rigid container, a stage for the cosmic drama. But that seemed strange when you really thought about it. What is this container made of? What is it? Does it exist? And then came the lightning bolt of genius. What if, Einstein thought, the gravitational field and space are actually the same thing? What if space isn't an empty, passive stage, but a dynamic, physical entity that can bend, stretch, curve, and warp? This was the revolutionary core idea of general relativity. In this new picture, the sun doesn't pull the Earth with a mysterious, invisible force reaching across millions of miles of empty space. Instead, the sun, because of its immense mass, creates a deep curve in the fabric of spacetime around it, like a bowling ball sitting on a stretched rubber sheet. The Earth isn't being pulled by some mysterious force, it's simply following the straightest possible line through this curved space, like a marble rolling around the inside of a funnel. Gravity is not a force at all. Gravity is the curvature of space-time itself. This beautiful and radical idea led to a series of predictions that sounded like pure science fiction. It predicted that starlight would actually bend as it passed by the sun, which was spectacularly confirmed during a solar eclipse in 1919, making Einstein an overnight celebrity. It predicted that time itself runs slower, closer to a massive object. A clock sitting on the floor literally ticks slower than an identical clock sitting on a table, an effect so real that our GPS satellites have to correct for it every single day, or they'd give you completely wrong directions. It predicted that when a massive star dies, it can collapse under its own immense weight and warp spacetime so intensely that it literally tears a hole in the fabric of reality, a black hole. And it predicted that the entire universe is expanding, born from a single, incredibly hot and dense point 14 billion years ago, the Big Bang. One by one, every single one of these seemingly insane predictions has been proven true through observation. Einstein had completely redrawn the cosmos. Newton's rigid, fixed stage was gone, replaced by what Einstein whimsically called a mollusk, a flexible, dynamic, living entity. The world was no longer particles and fields existing in space and time. Space and time themselves were now part of the fields. They were physical, dynamic, changeable. But even as Einstein was putting the finishing touches on his masterpiece, the seeds of a second great revolution were already sprouting. And this one was so deeply strange, so profoundly unsettling, that even Einstein himself would refuse to accept it. This was the birth of quantum mechanics. It began, as great ideas often do, with a small, stubborn puzzle that refused to go away. Physicists in the early 1900s were studying how hot objects radiate energy, things like glowing coals or the filament in a light bulb. To explain the experimental data they were collecting, a German physicist named Max Planck had to resort to a strange mathematical trick. He assumed that energy was not emitted smoothly and continuously, like water from a faucet, but in tiny, discrete packets, which he called quanta, meaning amounts. He thought it was just a clever calculation tool, a mathematical fiction with no connection to reality. But 5 years later, in one of his other revolutionary papers from 1905, Einstein showed that these quanta were absolutely real. He used the idea to explain something called the photoelectric effect, where light hitting a metal surface can kick out electrons. He argued that light itself is made of tiny particles, discrete packets of energy, which we now call photons. The granularity that Democritus had dreamed of 25 centuries earlier was back with a vengeance, but now it applied not just to matter, but to energy and light itself. This discovery opened the floodgates. The Danish physicist Niels Bohr applied the revolutionary idea of quanta to the structure of the atom. He proposed that electrons couldn't just orbit the nucleus at any random distance, like planets orbiting the sun. Instead, they could only exist on specific, allowed orbits, like steps on a staircase, each with a specific, discrete energy level. Electrons could jump from one orbit to another, releasing or absorbing a quantum of energy, but they could never, ever be found in between. These were the famous quantum leaps. This was deeply bizarre, but it worked perfectly. It explained with stunning precision the colors of light emitted by different elements when you heat them up. But the big question remained, why? What did it all mean? What was really going on? The key insight came from yet another young German genius, Werner Heisenberg, who was just 25 years old at the time. One night, walking through a dimly lit park in Copenhagen, he watched a figure appear under one street lamp, vanish into the darkness between the lights, and then reappear under the next lamp. He thought to himself, of course the man didn't actually disappear while walking through the dark patch between the lamps. He's a large object, and I can easily imagine his continuous path through the darkness. But then a radical, almost heretical thought struck him. What if tiny objects, like electrons, actually do disappear? What if an electron doesn't have a definite position at all when we're not looking at it? What if it only materializes, only becomes real, in a specific place, at the precise moment it interacts with something else? This was the mind-shattering core of quantum mechanics, and it changes everything. An electron isn't a tiny billiard ball following a neat, predictable path through space. It's something far stranger. A cloud of possibilities, a wave of potential. When you're not interacting with it, when you're not measuring it, it doesn't exist in any one specific place. It's smeared out across space, in a ghostly superposition. It only appears at a specific, concrete location when it collides with something, when it interacts, and where it appears is governed not by certainty, but by pure, irreducible chance. The theory can't predict with absolute certainty where the electron will be. It can only tell you the probability of finding it here or there. Reality itself, at the quantum level, is fundamentally probabilistic. This led to the third key feature of the bizarre quantum world. Reality is relational. Things do not have definite properties all by themselves, sitting there in isolation. An electron doesn't have a position, period. It only acquires a specific position in relation to the thing that measures it. The properties of the world are not written on objects like labels. They exist only in the interactions between things. The world, at its most fundamental level, is not a world of solid, independent objects. It is a world of events, of relationships, of interactions. As the theory rapidly developed, physicists realized that this strange quantum behavior applied to absolutely everything, not just electrons. Fields, too, exhibited this quantum nature. The electromagnetic field, which Maxwell beautifully described as a smooth, continuous wave, was also made of discrete quanta, photons, little packets of light. And particles, like electrons, were also quanta of their own matter fields, spreading out like waves of probability through space. The old, clear distinction between particles and fields completely vanished, blurred into irrelevance. The world, it seemed, was made of just one type of entity, the quantum field. So by the middle of the 20th century, physics had given us two spectacularly successful, yet profoundly and stubbornly contradictory pictures of reality. On one hand, there was Einstein's general relativity, a majestic world of smooth, curved spacetime, where everything is continuous, deterministic, and flows with elegant certainty. On the other hand, there was quantum mechanics, a world taking place in flat, unchanging space, where everything is granular, probabilistic, and only becomes real through the act of interaction. You can see the massive problem here. A student learning relativity in her morning class and quantum mechanics in her afternoon class would think her professors hadn't spoken to each other in a century. The two theories simply don't fit together. This conflict is the central, grand, unsolved problem of fundamental physics today. This is the desperate search for a theory of quantum gravity. This is where Carlo Rovelli and his life's work, loop quantum gravity, finally enter our story. The central idea of loop theory is breathtakingly simple, and it follows directly, almost inevitably, from the two great theories we've just explored. Let's follow the logical thread. Einstein taught us, beyond any doubt, that space is not a fixed passive background. It's a physical, dynamic field, the gravitational field. Quantum mechanics taught us, equally convincingly, that all physical fields are made of quanta. They're not smooth and continuous, but granular at the tiniest scales. If you take these two rock-solid ideas and put them together, the conclusion is absolutely inescapable. Space itself must be made of quanta. Space must be granular, like everything else in the quantum world. There must be atoms of space, indivisible building blocks of reality itself. Loop quantum gravity describes this granular, quantized space with a beautiful and surprisingly simple mathematical structure called a spin network. Imagine an intricate web made of nodes and links, like a cosmic spider's web. The nodes are the elementary quanta of volume, the smallest possible specks of space, the atoms of space. The links connecting them don't represent distances in the traditional sense. They simply tell us which nodes are adjacent to which other nodes, which quantum grains of space are touching. And here's the truly mind-bending part. This network isn't sitting in space. This network is space. The very fabric of reality, the stage on which everything happens, is woven from these finite, discrete, quantized relationships. This means there is an absolute minimum possible size, a minimum possible volume, known as the Planck scale. It is a scale so fantastically, almost incomprehensibly small, that if you were to magically magnify a single atom to the size of the entire observable universe, billions of light-years across, the Planck scale would still be smaller than a single tree. Below this unimaginably tiny scale, the very concept of space, as we understand it, breaks down completely. It becomes meaningless. And with this, Zeno's ancient paradox is finally, after 25 centuries, physically resolved. Achilles doesn't have to cover an infinite number of ever smaller distances to catch the tortoise, because infinitely small distances simply do not exist in our universe. The division stops. Reality is fundamentally granular. But what about time? Einstein taught us very clearly that space and time are inseparable, woven together into spacetime. If space is a quantum network, a granular web of relationships, what on earth happens to time? This is where the theory takes its most radical, most philosophically challenging leap. In the fundamental equations of loop quantum gravity, the variable representing time, the letter t, that has appeared in every single equation of physics since Galileo first started studying motion, simply vanishes. It disappears completely. Now, this doesn't mean that nothing ever happens. That would be absurd. On the contrary, it means that change is fundamental to reality. But it's not a change that happens in time, like a river flowing past you. At the most fundamental level of reality, there is no master clock ticking away, no universal river of time flowing at the same rate for everyone. The world is a dance of elementary events, a constant, ceaseless transformation of these spin networks. The theory describes these transformations using mathematical objects called spin foams. A spin foam is essentially a history of a spin network, a sequence of quantum events where the individual grains of space interact with each other, combine and merge, separate and split, in a bubbling, foaming dance of quantum geometry. So where does our familiar, everyday sense of a flowing time come from? If time doesn't fundamentally exist, why do we so powerfully experience it? Rovelli suggests that time is an emergent property, something that arises at large scales but doesn't exist at the fundamental level. It's much like the concept of heat. A single molecule jiggling around doesn't have a temperature. Temperature is a property that only makes sense when you have many, many molecules, and it measures the average motion of all of them together. In exactly the same way, time might be an effect that emerges only at our macroscopic everyday scale, a result of our necessarily blurred, incomplete vision of the incredibly complex, intricate dance of countless quantum events happening beneath the surface of reality. Time, in this radical view, is a form of ignorance. It's born from the fact that we simply can't see or track the individual quantum events. We can only perceive their statistical, smoothed-out average behavior. And that average looks to us like the flow of time. This radical new picture of reality has some truly profound implications that reach into the deepest questions of cosmology. It suggests that the Big Bang, the birth of our universe, was not a beginning from an infinitely dense mathematical point, a so-called singularity, where the laws of physics break down. Because space itself has a minimum size, the universe could not possibly have been squeezed into a point of zero volume. That's physically impossible in this theory. Instead, loop quantum gravity suggests our universe experienced what's called a big bounce. Our currently expanding universe may have emerged from the collapse of a previous universe, which reached the absolute minimum possible size allowed by quantum geometry, and then, like a compressed spring being released, rebounded violently outward, creating the Big Bang we observe. The theory also completely changes our picture of black holes, those mysterious cosmic monsters. The singularity that Einstein's general relativity predicts, sitting at the very center of a black hole, an infinitely dense point, also disappears in loop quantum gravity. Instead, matter falling into a black hole is squeezed and compressed to an incredible, almost unimaginable density, but still a finite density. And then, due to quantum pressure pushing back, it bounces. But here's the truly wild part. Because time near a black hole is so extremely distorted and slowed down compared to the rest of the universe, this bounce, which might happen very quickly from the perspective of the matter itself, could take billions and billions of years to unfold from our perspective watching from the outside. This opens up the absolutely mind-boggling possibility that black holes are not eternal, unchanging prisons from which nothing ever escapes. Instead, they might eventually explode in a spectacular burst of energy, releasing back into the universe everything that ever fell inside. This would be one of the most dramatic events imaginable in the cosmos. Ultimately, this long, winding journey from Democritus on his ancient ship to modern quantum gravity leads us to a new, surprisingly simplified and deeply strange vision of what the world really is. All the old familiar ingredients, solid space, flowing time, concrete particles, and smooth fields, have dissolved away like mist in the morning sun. What remains is a single, unified substance, covariant quantum fields. These fields are not sitting in space or unfolding in time. They actually generate space and time through their ceaseless probabilistic relational dance. The world is nothing but a swarm of elementary events, a foaming of spin foams, a shimmering network of relationships. And that's it. That's reality. So what are we supposed to do with a vision of reality this strange, this utterly far removed from our everyday common sense experience? What's the practical lesson for us, living here on this seemingly solid earth, moving through this seemingly steady flow of time? The most powerful lesson in Carlo Rovelli's work, I genuinely believe, is a profound sense of humility and wonder. He shows us, with crystal clarity, that the world as we perceive it is absolutely not the world as it actually is. Our senses, our intuition, our so-called common sense, these are tools that millions of years of evolution have given us to survive on the surface of our particular planet. They're incredibly effective for finding food, avoiding predators, and navigating our immediate environment. But they give us a deeply limited, parochial, provincial view of reality. They show us a flat Earth when it's actually a sphere. They show us a stationary world when we're actually hurtling through space at incredible speeds. They show us a universal now when no such thing exists. And practically all of it is misleading or flat out wrong. Science, as Rovelli beautifully demonstrates, is the systematic process of questioning these deeply ingrained intuitions. It's the art of learning to see further and more clearly than our limited senses allow. The entire story of physics is a story of one veil after another being lifted from our eyes, revealing deeper layers of reality. Anaximander showed us that the sky doesn't just stop at the ground, it continues beneath our feet. Copernicus showed us that we're not the center of everything, but rather we're riding on a spinning rock hurtling through space. Einstein showed us that time is not universal and absolute, but flexible and relative. And quantum mechanics shows us that reality itself, at its core, is not a collection of solid things, but a ghostly dance of probabilities and relationships. With each new discovery, the world becomes stranger and more counterintuitive. But here's the beautiful paradox: it also becomes more elegant and more beautiful. There's a deep aesthetic pleasure in the idea that the vast, complex universe is woven from a surprisingly simple set of fundamental rules, that all the incredible complexity and richness we see around us is born from the endless combinations and interactions of just a few fundamental ingredients. Democritus's alphabet of atoms has evolved into the shimmering, interacting quantum fields that write the epic, unfolding poem of the entire cosmos. For a young person standing at the very beginning of their life's journey, this perspective has both practical and, I would argue, deeply spiritual significance. It teaches us not to trust blindly in what seems obvious or self-evident. It teaches us that our most deeply held, unquestioned beliefs about the nature of the world might be completely wrong. And far from being a reason for despair or cynicism, this realization is the very source of progress, discovery, and genuine wisdom. As Rovelli reminds us with beautiful simplicity, science is not nourished by certainty. It is nourished by a radical distrust in certainty. So how can you actually apply this perspective in your own life? You can start by actively cultivating your own sense of wonder about the world. Look at the everyday things around you and consciously remember the hidden, strange reality beneath the familiar surface. When you see a sunbeam slanting through a window on a dusty afternoon, remember that it's actually a shower of billions upon billions of individual photons, tiny quantum packets of light that have traveled 93 million miles through the vacuum of space to reach your eyes in that moment. When you feel the solid, reassuring weight of a stone in your hand, remember that it's not really solid at all. It's a monotonous process, as Rovelli puts it, a temporary, ever-changing configuration in the ceaseless vibration and interaction of quantum events. And when you feel the inexorable, seemingly unstoppable passage of time, that feeling of moments slipping away forever, remember that this might be nothing more than an emergent illusion, a measure of your own ignorance of the world's hidden microscopic quantum dance. Most importantly, embrace uncertainty. The world is absolutely full of people who claim to have all the answers, who speak with absolute confidence about how things are. But the truly greatest minds in all of human history, from Socrates walking the streets of Athens to Einstein working out his equations, these people were defined not by their certainty, but by their acute, honest awareness of their own ignorance. True wisdom is not about knowing everything. It's about honestly knowing what you don't know. And it's this awareness, this intellectual humility, that is the real engine of discovery. It's the deep curiosity that drives us to look over the next hill, to ask the next question, to continue this magnificent 2,500-year-old journey of understanding that began with a man boarding a simple wooden ship in the port of Miletus. The universe is not just stranger than we imagine. As the scientist J.B.S. Haldane once said, it's stranger than we can imagine. And the ongoing exploration of that profound mystery is one of the most beautiful, meaningful adventures we can possibly have as human beings. That was a summary of Reality is Not What It Seems by Carlo Rovelli. We've explored the grandest, most mind-bending ideas from this incredible book today. But I need to be completely honest with you. A summary can only ever be a rough map of the territory. The real treasure, the real magic, is found on the journey itself. The true transformation happens when you actually read the book, when Rovelli's elegant prose and his brilliant, illuminating analogies click into place in your own mind, and you feel that almost electric sense of awe as a genuinely new understanding of the world dawns on you, changing how you see everything. Think of this podcast as a doorway, an invitation. If any of the ideas we've discussed today, the granular structure of space, the disappearance of time, the possibility of a big bounce instead of a big bang, have sparked even the smallest flame of curiosity in you, I absolutely encourage you to step through that doorway. Grab a copy of the book, settle in somewhere comfortable, and really engage with it. Because reading it isn't just about passively learning facts and theories. It's a genuine experience that has the power to fundamentally change the way you see your place in this strange and beautiful cosmos. You can find a link to the book right there in the description below. Also, if this journey into the deepest nature of reality has been valuable to you, if it sparked something in your mind or made you see things differently, please take just a moment to hit that like button and subscribe to our channel, Billionaire's Bookshelf. That way you won't miss our next exploration into another book that has the potential to genuinely change your life and expand your understanding. Let's keep learning, growing, and discovering together.